Benchmark was primarily set up to collect prices and produce price assessments for what we've termed the critical minerals in the lithium-ion battery supply chain. So we do monthly price assessments for lithium, cobalt, graphite, and more recently nickel. We also do monthly market assessments, the battery Megafactories report I do, which I'll be talking about today. We also do similar assessments for the cathode and anode market. We also offer a range of forecasting consultancy services, a number of events each year, the Benchmark World Tour. Funnily enough, travels around the world every year, about 15 cities globally. And we also have 2 industry conferences that we've just wrapped up in LA. I got back on Monday. So how do we go about collecting our data? We don't do that from behind a desk. A lot of the data we collect ourselves in person at the mines, the refining plants. Photo here from a research trip to the Tesla Gigafactory we did earlier this year. And that's kind of helped build our reputation through the supply chain. We were lucky enough to be invited to give testimony to the US Senate twice, once in 2017 and once more recently, I think February or March this year. Also, just 2 weeks ago, some members of the team were at the White House and the Pentagon talking on exactly this, lithium-ion battery supply chains. Okay, so moving on kind of into the meat of my presentation. We, as a company, have been tracking the build-out of lithium-ion battery production facilities since 2014. And here I've taken a snapshot of data from the first quarter in 2015. We were tracking just 3, what we term battery megafactories. These are battery plants with a capacity of greater than 1 gigawatt hour. The reason we tracked them was because prior to that, everything was at the megawatt hour scale, and all of a sudden, Tesla, Foxconn, and LG talked about plants at the gigawatt hour scale. So 3 plants at the time, back in Q1 2015. We're now tracking over 2 terawatt hours of capacity, over 100 plants to be online by 2028. Just some of the names there, obviously the big names that everyone knows, and perhaps some that people don't. So huge amount of growth in that supply chain, huge amount of investment, and how does that picture break out? So as I said there, we tracked 104 plants in our most recent assessment, up from around 1.5 terawatt hours to 2 terawatt hours since Jan 2019. That represents around $40 billion of investment to add that extra half terawatt hour capacity. So no shortage of money flowing into this part of the supply chain, which can't be said for other parts. So this is kind of the regions where we see that capacity built out. The kind of takeaway from this slide is that China remains dominant throughout the whole period. So around 70% of that capacity is going to sit in China for the next decade. And we can also see the build out of Europe, so going from 6.7% to 15.9% over the time frame, and that's obviously related to proximity to customer. So some big automakers in Europe, but also certain parts of Europe we think cost of production is second only to China. But the caveat to that is, Eastern Europe particularly is where we're seeing cheap production. The caveat to that is that we're seeing huge incentives put in place by governments to try and attract what's kind of new automaker money, bringing the auto industry to their country, whereas before we've had very established supply chains which aren't going to move. This is an opportunity for some countries to try and bring some of that money to their own countries. And that's what we're seeing, these huge incentives throughout Europe. So 2 terawatt hours by 2028 to 2,000 gigawatt hours is a big number. It's probably ahead of a number of different forecasts, and there's a couple of reasons for that. Obviously, demand can't be fulfilled if the battery plants aren't there to make the batteries. The other thing that we've looked at closely is we've started ranking the battery plants by tier. So this relates to whether the companies who have the plans have been qualified by multinational OEMs, by that I mean automakers outside of China, to provide them with cells. So really what they need to be able to do is deliver tier 1 quality at tier 1 volume. So it's not just a quality thing, it's also being able to deliver at volume. And you can see from the chart, only around 30% of that capacity has been qualified. So 70% of that 2 terawatt hours still needs to be qualified by automakers, which is a very long process. Takes, well, I think best case scenario would probably be 9 to 12 months, but it can take much longer as a completely new producer. Even incumbent producers, when they build a new plant, will still need to qualify cells from that plant with an existing customer. So it's no easy feat, and it means basically that of that 2 terawatt hours, not everyone's going to make it. They're not going to make it on an economic basis, and they might not be able to scale up and produce batteries at the quantities that they need to fulfill the contracts they've made with automakers. And what will they be using in terms of raw materials, or what cathode will they be using to go into their batteries? So here is we, as part of the report that we do, we forecast the cathode material they'll be using. And you can see, despite quite a lot of reports in the media, only a very small percentage of them right now can produce 811 cells. Now that's going to grow. That's certainly a trend. You can see the yellow here. So this is NCM 111, even parts nickel, cobalt, manganese, 523, 622, and 811. So largely speaking, they're all going to have, or a large portion of them are all going to have nickel and cobalt, even NCA here, still going to be quite big. But the transition to high nickel cathode, 811, is going to take a lot longer than people think. One of those reasons is quite simple. You've seen a huge capacity build out for the other cathode types, and people aren't going to turn those off and all of a sudden start building new lines for 811. It requires slightly different production technology. So there's an infrastructure build out, but also there are challenges around producing that. There's safety challenges and life cycle challenges which still haven't been overcome to satisfy the needs of kind of multinational automakers. Some of that cathode is being deployed in EVs in China, but outside it hasn't happened yet. And even if you think that I'm wrong and NCM 811 is already a huge part of the market, as part of the cathode market assessment we only see 8% of cathode production capacity dedicated to 811 now. So again, there's still an infrastructure build out throughout the supply chain to move to these really high nickel, low cobalt cathode types. So raw materials, I guess that's kind of the question that people here want to know is how much of these raw materials are going to be needed in the future. So the numbers here are actually taken from the battery megafactory. So we assume 100% utilization for these numbers, which obviously won't happen. No one, although they would like to, they're never going to achieve 100% utilization. So the numbers are slightly higher than what would actually be achieved, but it shows you the type of growth rates that we're going to see just to fulfill these battery plants, which we think have a realistic chance of getting into production. So graphite anode up 7x, lithium up similar numbers. So going from around 400,000 tons for graphite, maybe 250, 300,000 tons for lithium, going all the way up to 2.5 million for graphite and around 1.75 for lithium. Nickel up much more, but that's partly because it's coming from a much lower base. And then cobalt up 4x as well. That's partly to do with the substitution towards more nickel-rich cathodes. So, the key thing to think here is that even with cobalt, up 4x, which compared to these other numbers looks quite low, that means every 2.5 years you need to double the amount of material that can go to the battery supply chain. It's a huge challenge for the industry, particularly with commodity prices where they are today, for lithium and for cobalt and nickel on its way down as well. So we're not seeing the investment go into the supply chain now that's needed to fulfill this. So there's a big disconnect between the upstream and the downstream, the $40 billion that I talked about going into the battery plants. And these raw materials have become so important to the automakers that we're seeing a complete change in the way that they purchase their raw materials. So historically, from those that produce EVs, essentially what they've done is, as an automaker, they've just gone to their cell manufacturer and bought cells. And in those cells, they get the raw materials that they need. Obviously, the cathode contains the materials. But that isn't the best way to do it for them for two reasons. One, it's high risk. If the cell manufacturer doesn't sign the contracts that they need to deliver on their for their customers, then they're left without cells. But also they end up paying a bit of a premium throughout the supply chain. Every person that's taken the risk on raw materials will add a slight premium for the fact that they've bought some cobalt and stuck it in their warehouse, or some lithium and stuck it in their warehouse. So what we're actually seeing now is the auto industry is going all the way back to the mine level. So these are kind of some of the key players in those supply chains. And they're speaking to them directly about securing raw materials. So it's a complete change in the way that the automakers have secured these battery chemicals, and it just goes to show how important they are. They're kind of at the top table of the boards of these automakers, at the top table of geopolitics. So they're rising in importance, and at the moment we're still just at the advent of the kind of birth of this industry. And why is it important? So I did some analysis here. We have a battery cost model, and I wanted to show the relative sensitivity in changes to the raw material inputs of what it means for the total cost of the cell. Now, this is the cost of the cell. This I put here, cell cost. Important to explain, that's just bill of materials and cost of manufacturing. Doesn't take into account things like tax or margin or depreciating assets over time. It's just changing the raw materials. It's based on a large battery production facility in China, so it uses power inputs and stuff based on the Chinese market. So as a base scenario, I've took the prices from the most recent benchmark assessments for cobalt sulfate, nickel sulfate, and lithium carbonate. These are the prices here, and it spits out a cell cost of just over $100 per kilowatt hour. Now, this is a large plant operating at high utilization, is the assumption. And that's, realistically, there are some automakers that can achieve cell costs, some cell makers that can achieve cell costs in this region. Then I've put scenario 2, I've called Armageddon. Now, that is the recent multi-year highs for all of these commodities. You can see, obviously, cobalt going all the way up to $22.50 a kilo, cobalt sulfate, that's per ton of sulfate, not per ton of cobalt contained. That has a big impact on the cell cost. Sorry, I should add as well, this is for 622 pouch cells, so quite nickel rich, kind of forefront of modern technology today. So put up the cost of the cell in that Armageddon scenario by about 46%. Then I've put scenario 3, what I've termed volatility as norm. So I think cobalt and lithium prices are probably relatively low. We're in the low part of the cycle right now. Nickel is, from when I did the price assessment that I took the data from, was probably a bit above where I think it will be kind of in the near term. So I put that down by 20%. You can see 8.4% impact on the total cell cost, up to around $110 per kilowatt hour. Then finally, I kind of looking slightly further forward, as the nickel market starts to tighten, I've assumed that the cobalt and lithium prices stay flat. Reality is they probably won't. But putting that nickel price up as well puts it up by 15%. Now, probably doesn't sound that significant, but that's more than the margin that these automakers are aiming to make on EVs. So getting your raw material sourcing strategy right and being able to stabilize some of that volatility, partly through long-term offtake contracts with direct at the mine level, which is what we're seeing happening today, is one of the key strategies that we're seeing deployed by automakers to do that. Now, the problem they have is automakers are not bringing in a new product. They're bringing in a competing product. It has to compete on price with an ICE vehicle. You're not going to go and buy the ID3 if it's $50,000 if you can buy a Golf at 30. No one's going to do that. It's the same car, essentially. So they need to bring the cost as close as possible to the current ICE vehicles, and they need to fix that cost for a year. So that's the huge challenge that automakers are facing. And if they get it wrong, essentially, they're going to go bankrupt. We've had huge automakers say that to us, like, this is it. If we get this wrong, that's the end of the company. It's company-ending stuff. So very important, and something we're involved in with a number of different companies. So I put this slide in here. This is some analysis that we did on the average cost of a lithium-ion battery for the last 5 years. You can see dollars per kilowatt hour here. The battery costs, very clear trend year on year. Despite huge raw material cost volatility, they've continued to fall. Now, a lot of that has come from essentially scale. So we've seen much bigger battery plants come online over the last 5 years, particularly in the last couple of years. And as you add scale, you get economies of scale, and the cell costs have continued to fall. We've got slightly better at producing batteries, more smart, more efficient, and they've been able to do that despite this volatility in the lithium and cobalt price. As we get down here, that's going to become more challenging, and so the total cost of the cell is going to be more closely linked to the cost of the raw material inputs going forward. So again, that's a very big consideration for the market. They've been able to kind of be slightly more relaxed because we've kind of picked a lot of the low-hanging fruit on reducing your cell cost. But as time goes on, we're going to see a much tighter correlation between raw material input costs and the total cost of the cell. Okay, so this is, again, probably something that the room here are probably more interested in. We did some analysis on the lithium-ion battery critical raw materials, so the 4 critical raw materials here, based on our 2030 demand projections, how much investment are needed in each of these markets to meet that to produce enough material to fulfill that demand. Kind of the standout, sorry, this is for capex for building mines. So the standout value here is $50 billion needed in the cobalt market to meet the forecasted cobalt demand. Now that is obviously not happening at the moment. It's slightly different because obviously cobalt's a byproduct, so really you're building big nickel and copper mines, but around $50 billion to meet that demand. 39 billion in the nickel market, 24 billion in lithium, and 13 billion in graphite. So as I kind of mentioned earlier, at the moment, despite seeing more than this total capex combined deployed into the batteries production capacity part of the supply chain, we're not seeing that happen in the raw material markets now. That also presents an opportunity. It's a great time to invest. Prices are relatively low, but of course it's quite scary, and it's probably as always relatively high risk. But it just goes to show you that the market has a long way to go to meet. Even 10 years away, it's not that long in mine terms. That's essentially a discovery and a build out of a mine, generally speaking. So a big challenge for the industry at the moment, and something that as time goes on, we're kind of missing that more and more. So in summary, we've seen a huge investment in the battery supply chain in certain parts, production of EVs, production of batteries, but we're really not seeing that go through to the upstream. Key things, I think takeaways would be that whilst there's probably quite a lot of misinformation out there about the transition to high nickel cathodes, NCM 811, the reality is that that's going to be a long tail. It's going to take a while. It's going to be gradually introduced. There's still some engineering challenges around that. But also, we're not seeing current capacity for kind of the 523, 622 part of the market being bought offline. People tend to be adding either new plants or new lines. So, that's going to be a gradual build out of infrastructure that's going to take a while. And I think really don't underestimate how slow this market will respond to changes like that. It will happen, but it's going to take longer than people talk about. And ultimately we're seeing much more interest from automakers on this part of the supply chain, the upstream, trying to secure raw materials, and we're seeing strategy move certainly to communicate more directly with the upstream supply chain and try and secure long-term offtakes. But with current raw material prices, we're not seeing enough capital flow into this upstream part of the market, and that's something that is going to have to change if we're going to fulfill the demand projections. I've gone through that quite quickly. I've left some time at the end for questions, so hopefully there's some questions on the floor.
So I fear I may be starting with a very basic question, but
yeah.
I don't really understand the difference between the anodes and the cathodes. I mean, I know from school chemistry roughly what an anode and cathode is, but
yeah.
You're talking about the anodes being mainly graphite, but the cathodes are where you have all the more sort of complicated formulation. Is that right? And perhaps you could explain why.
So so obviously you have a positive and negative terminal in a battery depending on the state of charge, which one's positive and negative, but the cathode is where you get the nickel, cobalt, manganese, and that's I'm not going to say either is more important, but what we've seen more recently is a lot of focus on the cathode side of the market to improve energy density. Anodes tend to exclusively be made of graphite, a mix of synthetic and natural graphite, and some silicone doping we're starting to see come into the industry now. But typically we've seen, recently there's been more focused on the cathode side. That's where we've seen this kind of move towards more nickel rich. But with the anode, we're now starting to see renewed interest because people have realised that as we're asking for more from the cathode, it's getting more challenging, where there's still a lot of R&D work that can be done on the anode and get better performance out of the battery.
And so would improving the anodes improve energy density as well?
Yes, it can, and also charge rates and various other factors. But so getting better performance out of the anode is just as valuable as getting better performance out of the cathode.
Caspar, it seems to me that copper is essential, nickel is essential, lithium is essential, but wouldn't the automakers be spending a lot of time trying to replace the cobalt or and is graphite really essential? Isn't there lower cost options for auto manufacturers to the graphite?
Graphite's not that expensive at the moment. I mean, cobalt, there's people talk about removing cobalt from the cathode entirely. I think that's going to be extremely challenging to do, because it doesn't just provide kind of a safety stabilizing element, it actually provides a certain structure to the cathode and the kind of crystal scale. So when you remove that entirely, the nickel wants to deform and the battery doesn't perform as it needs to. It doesn't live as long, essentially. So that's very challenging. There are people working on that, but I think realistically for it to be commercially viable, it's a long way off, and I still have my skepticism. Graphite, there are other options theoretically. If you look at solid state batteries, which the leading ones use kind of current cathode technology, they use a lithium metal anode, but they are a long way off commercialization. We're talking more than 10 years. So at the moment, I would say I'm fairly confident in saying that I don't think there'll be different slight changes in kind of the recipe of what goes into the batteries, but the raw materials that go in now are not going to change in the next decade wildly. There'll be slight changes in like doping and things like that, but I don't think they can be changed that easily.
So you don't think that cobalt will be replaced in the batteries?
I think it's very unlikely at the moment, yeah.
Okay.
It's very challenging.
The other thing, you made an allusion to the auto manufacturers. If they didn't adapt to the EV revolution, that they would go broke. Which is the slowest to adapt to the automotive manufacturers?
Oh, I'm not going to name names.
Oh, come on, Caspar.
You can Google that. I mean, there's some that are certainly ahead. The ones that have made the big investments, like VW, is very obvious that they're pouring money into it. But certainly, if it's not only the fact that, well, a lot of it is to do with meeting emissions targets, right? So if you don't do it, you're going to face billions in fines. So they kind of have to. They're being forced to. But yeah, I'm not going to name any names, but there are some that are further ahead, and there are some that will probably go bankrupt, and I'm not saying that they will then disappear off the face of the earth.
Just looking for what to short.
Right, okay, yeah, no, I'm not going to name any names.
How do you see the CO2 footprint and the environmental issues? Producing electric cars seems to be nice, but if you have a problem with the CO2 footprint and environmental issues, that is another reason.
What, as in of producing an EV? Is that as in, I know there's some information out there was historically about saying that actually over the lifetime of an ICE vehicle and an EV that the CO2 emissions are greater. I mean, can you really do the assessment on that, considering that these supply chains, EV supply chains, are very immature at the moment. They're very inefficient, and they will have to become more efficient to do what they as they scale, they will. Also, EV production is at a very limited scale, and it has typically been ICE vehicles that have had batteries kind of crammed into them and made them electric vehicles. That's changing now. We're starting to see from the ground up EVs, which are going to be far more efficient to produce. And of course, there's the other argument would be like if you have dirty power going into the EV, i.e. from coal-fired power stations. But chicken and egg scenario is that for us to move to transition to renewable energy, intermittent power, you need batteries. And those batteries need to be efficient on cost. But once we do that, we can have an entirely renewable ecosystem theoretically.
I think part of that question was related to the carbon footprint of the carbon, the nickel, the graphite to get to that point, and under a life cycle assessment, which the OEMs are looking for to say, well, what is the carbon footprint of this raw material I'm putting into a battery?
I don't. We don't do that analysis. We don't. We do prices and raw supply and demand. But yeah, I mean, mining's a dirty business, right? But what are cars made out of? Minerals, essentially. They're metals primarily. But that's part and parcel of the way things are. And obviously, the supply chains, as they become more efficient, that will become cleaner, and there'll be less transport involved. If you look at the supply chains of batteries, historically they go all around the world several times. But that's becoming, as we're seeing battery plants, cathode plants and precursor manufacturers being built throughout different global regions other than China, that will become more efficient as well.
In terms of recharging points, I think I'm right in saying at the moment you need a 30 amp supply to recharge a car. Would that be right? Or?
You can charge off, you plug it into your plug in the wall in your house. Okay. It'll just take a long time, yeah.
Okay. I mean, point one, I mean, do you look at the implications of EVs on the need to upgrade the grid? Have you got any numbers on that?
That's a bit downstream for what we do. We have a company, we have a kind of sister company that does look at that. But yeah, I mean, there's argument that I think, you know, the national grid is fine. The problem is when you get to the substation to go to residential areas that it's overload. You know, they're built in the 50s to allow for you to turn your kettle on your TV, right. Whereas now it's a totally different kettle of fish, and there will need to be some investment. But there's a number of other options that can help, you know, manage some of that.
Do you think the national grid is up to carrying it?
Yes, but I am no expert.
Okay.
From what I understand.
And is there anything changing in the way batteries are made that will change how quickly they can charge or whatever? I mean,
that is obviously fast charging is like a real big goal of the EV industry. Now there is a way you can do that, but really what you actually are doing is just putting more batteries in the car. You can make it appear as though it fast charges, but in reality you're just using more batteries to use the kind of maximum charging window. But that is one of the big focuses of the industry. The issue you have with lithium-ion batteries of today is that it uses a liquid electrolyte, and that's what catches on fire if you charge too quickly or the battery fails. And that's essentially the issue in terms of like battery fires and fast charging. Theoretically, you can get over some of that problem with solid-state batteries. Yet it hasn't been proven at commercial scale, or still, you know, we don't really know exactly how that will work. But there's theoretically you could do that, but at the moment no one's cracked it. So that's the solid-state part of the reason why it's appealing, is you get rid of that liquid electrolyte, which is the dangerous part.
What do you see as the potential substitution effect from the work being done by MIT and others on batteries based on zinc and aluminium and so on?
So there's a lot of information in the media about kind of lab scale work being done on different battery types. I would say it's great work, and you know, there is something in the future, but anything that's at the lab scale today is at least a decade away from commercialization. That's an absolute minimum, I would say. If you think lithium-ion batteries were invented in the 70s in a lab, commercialized by Sony in the 90s, we're now 2020 essentially, and we're now at the stage where we can kind of use them commercially in vehicles. It's a very, very long. I mean, it would be slightly easier because we've electrified drivetrains and stuff like that in transport, but you know, those other technologies are all very challenging to bring to a commercial level, and also kind of beat lithium ion on cost as well. That's something else they'll have to do. They need to be either way more energy dense or, you know, out of the park better on certain factors. And you know, we think that the most promising of those is solid state for transport, which is, as I say, is decade plus away. And at the moment are still using the same cathode technology as current day lithium ion.
And a second question, just on the supply side, we saw with the cobalt price rising drastically, swing producers coming in from DRC, from the artisanal miners and so on. Do you look at that in your forecasting? We basically, as you get above a certain price, we believe that, you know, you will see an increase in DRC artisanal activity, but of course the industry is moving to bring that to a kind of accepted standard through model mines. So artisanal is not a problem. They're very poor people that are, what they mine today puts the dinner on the table tonight. So you don't want to take that away, but you need to ensure that it's happening primarily safely. You know, no child labour, no risk of mine collapse, no forced labour or anything like that. But obviously legally as well, they have the right to go there. So what we're seeing is the industry is moving towards that. So theoretically, yes, we actually want more artisanal, but it needs to be done in a safe way. But yeah, I mean, it's price-sensitive production, right, essentially, swing production. And in 2018, it was like the biggest year ever for artisanal production, theoretically.
Time for one more question we can squeeze in? No? I've got a question, actually. There was Rio discovered quite a large deposit of lithium in California recently.
Yeah, tailings, yeah.
Yeah. Do you think that signals of major miners taking more interest in battery materials? Could that kickstart things for lithium a bit more? Or what's your view on that?
I mean, I think, so like it's just like a soft entry into lithium. They've obviously got Yadar in Europe, which they haven't developed. But yeah, I think, you know, the major miners have very much have this on their radar. It's just like I don't think they really know how to get into it, because it's very tiny compared to the business they're doing elsewhere. And, you know, it's an easy way. Oh, we've got this tailings pile which has lithium in it. We can learn how to process lithium, but we're not really getting into lithium. We're just, you know, using some of our tailings, and it's a huge tailings pile, right? It's massive. So it's kind of, yeah, I think so. I think, you know, from my experience, all of the major miners would like to get in some way. Just at the moment, it's very hard for them to do that. Yeah, so kind of soft entry, yeah.
Exploring new ground, excellent.
Yeah.
All right, well, round of applause for Caspar, please. Thank you.
Thank you.